Welcome back. I'm not sure what day it is that you'll be watching this video, but for me, today is the vernal equinox. So, happy vernal equinox, everyone. Today we're going to be doing lecture number 19, which is a continuation of lecture 18. So this is all about the interference and wave nature of light, continued. Now, last time we looked at Young's double slit experiment, or what's sometimes just called the double slit experiment, where we had a laser over on this side that came, well, I've just changed the wavelength, there we go, that approached toward two double slits. They came through the double slits, they spread out, interfered with each other, and then formed this double slit interference pattern on a screen, say somewhere far from the slits. Now, one thing I want us to think about just for a minute here before we move on is, why does that light spread out like that? When we have a laser, we usually think of the laser as working. We usually think of lasers as working. This plug needs to be reset. There we go. We usually think of lasers as making a very, very small dot, so to speak, that then can go for a very long distance and still maintain a very narrow collimated beam. Why is it that these beams are actually spreading out and forming this extended pattern over on the screen with all of these bright fringes and dark fringes that all are spread out like this? Why do these rays spread out? And why is it that they only spread out in one direction, the direction where we have these bright fringes? Why don't they spread out this way as well? Well, this is a very, very interesting question. If we look at a beam of a laser, and I'm going to take that small dot and let's imagine we expand it. So I'm going to take this very narrow dot of a laser beam and imagine we enlarge it. What we end up with is a round beam, and if we could look at the energy distribution in this beam, it's not exactly contained within this circle where it's a uniform distribution inside and then zero energy outside. It actually looks more like a Gaussian. So it looks something like this. If that's the zero energy, the energy distribution looks something like this, where it's largest in the center and then decreases like a Gaussian or a bell-shaped curve as you move away from the center. Now, if you can imagine dropping a pebble in a body of water, you get these round ripples that are all centered on the point where you've dropped in the pebble, and the ripples then extend or expand outward. Okay? Now, we can think of every point on a beam of light as a source point for the beam in front of it, so to speak. This is called Huygens principle. So that every beam, every point on a beam, you can think of as a source for the next point that keeps that beam moving forward. Now, and then because of constructive interference and destructive interference, you get some areas where the beam continues and some areas where you don't get any beam because they all add together destructively. Well, the presence of these tails over here actually help keep that beam going in a very narrow straight line. These tails, even though they're getting smaller, they help that center stay together. Now, when we take a beam and send it through a slit, it's basically like chopping off the sides of the beam. We basically remove the sides of the beam in one dimension. So we don't have those tails in that sideways direction to maintain that beam. So what happens? The beam spreads out. So in the direction of the slit, so we're cutting off these sides, the beam is going to spread out that way. However, we still have the tails on the top and the bottom that maintain the beam vertically for our pattern where we had the the fringes laid out horizontally, it's still kept narrow in the vertical direction, but only spreads out horizontally. So that's a basic idea of why these beams are actually spreading out this way. And then the two beams interfere and give us the double slit interference pattern like we saw. Well, what if we were to take a beam and send it through just one slit? What if we took a beam and put it through only one opening? What kind of pattern would we get in that case? Well, let's try that and see. Okay, if you'll remember last time, we looked at the double slit experiment where we used these two slits. So we used, here's a slide with these 4 pairs of double slits, and we sent the laser through one pair of slits to form the double slit interference pattern. What we're going to do now is use a different slide. We're going to use a slide with only a single slit. So here we've got 4 single slits. So I'm going to send the laser through just one of these slits and see what kind of pattern we get now. So here we see the laser without the slit, and now I'm going to put the slit in front of it. And there we go. Now, what I want you to notice is, first, we do get an interference pattern. We get bright fringes corresponding to some kind of constructive interference. We get dark fringes, bright, dark, bright, dark, dark, bright, dark, bright. So we are getting some kind of spreading out. Again, notice the spreading out is in the horizontal direction. Because why? Because the slit is a vertical slit which cuts off the edges of the beam on the horizontal side, spreading it out this way, but not spreading it out this way in the vertical direction. We're getting it spread out, we're getting bright fringes, we're getting dark fringes. I also want you to notice that the central bright fringe, so this is where the beam originally was without the slit. We have a very large central bright fringe, but then the side bright fringes get smaller, but likewise they also get dimmer. So the central bright fringe is the brightest, and then as we move to the side, the bright fringes get dimmer and dimmer and dimmer. Now I'll actually try and turn the lights off and see if we can see this a little bit better. There we go. Hopefully you can still see that. Very large central bright fringe, dark fringe, bright fringe, dark fringe, and it extends off for quite a ways to the sides. Okay, so what's going on here? So now we've got a single slit set up with a screen. So similar to our double slit diagram. We'll define a central axis here, the line that's perpendicular to our slits here, or slit perpendicular to the slit, over to the screen, and here's our screen over here. And what we have is light coming through the single slit, coming up to some point P, which is then giving rise to a dark fringe or a bright fringe. Now, how is it possible that the light can actually interact with something and give rise to constructive and destructive interference? What is it interacting with? Well, it's interacting with itself. There is a slit here with light coming out of different parts of that slit. And light coming through different parts of the slit, either near the top or near the bottom, can interfere with other light through the slit to give rise to constructive or destructive interference. Let's enlarge this picture and kind of get an idea of what's happening. For light striking the center of the screen, in other words, the point near the central axis on the screen, we basically have all of the rays coming through the slit, coming through parallel, essentially parallel to each other, to come together at that central point. And if they're all parallel, they're all going to have the same path length, so there'll be no path difference. If they start out in phase, they'll end up in phase, and if they all end up with the same phase, they're going to combine constructively. So we would expect on the central axis to have a bright fringe, but that's exactly what we saw. At the very center of the pattern, we had that very, very large bright fringe. Now, what if we actually have a point off the central axis? Let's imagine we're looking at some point at some angle theta. Now, again, we're going to make the approximation that the screen distance what we called L before, we're going to assume that L is much larger than the size of the slit. So we don't have two slits to have a slit distance or a slit separation. We have a single slit. So let's imagine that the width of this slit we'll call W. So W is our slit width for a single slit. So let's imagine we're looking at some angle theta. The screen is very, very far away, so that L is much larger than W. So still, we can assume that all of these rays are going to be parallel to each other, but now they're going to be going off at some angle theta, let's say above the central axis. What happens now? So let's imagine we're looking at a point on the screen that is at an angle theta above the principal axis, such that the path difference now between a ray that comes out of the top of the slit and a ray that comes out of the bottom of the slit is one full wavelength. In other words, the ray at the bottom has to go an additional complete wavelength lambda farther than the wave coming out the top. Well, in that case, the path difference between the wave at the top and the wave coming out the middle will be a half lambda. So 1/2 of a wavelength. Well, what will happen when the wave at the top and the wave coming out the middle combine? In other words, a wave that's half a wavelength out of phase, well, when they will combine destructively. They'll cancel each other out. But what about a wave that comes out a little bit below and a little bit below here? Well, they will be a half a wavelength out of phase. They will combine destructively. What about here and here? Destructively, here and here, here and here, here and here, here and here, all the way down. For the top half, there's going to be another wave coming out the bottom half that's always 1/2 wavelength out of phase. And so there's always going to be another wave that will combine with the wave above and below. They'll combine destructively. So what will we find at that angle if all of the waves cancel out? We'll find a dark fringe. Well, now let's think about this. What we want then is a path difference from the top and the bottom, a path difference of lambda. Now, drawing the diagram very similar to what we did for a double slit, if this angle is theta, and this is perpendicular here, we know that that'll be 90 minus theta, that will be the angle theta. In other words, we can redraw this triangle. I'll redraw it right over here. We want this path difference to be lambda. This angle is theta. The hypotenuse, because this is a right angle over here, the direction, which is perpendicular to this side, is going to be perpendicular to here. That is the slit width. So what do we want? We want the opposite side over here, which is W sine theta. When that is equal to lambda, what do we find? We find a dark fringe. Very, very good. So we find a dark fringe when W sine theta equals lambda. Well, are there any other points where we'll get destructive interference? Well, yes, there are. Let's imagine we look at a steeper angle such that the path difference between the top ray and the bottom ray is 2 lambda. In that case, the path difference between the top ray and a ray coming out the middle will be lambda. The path difference between the top ray and a ray coming out 1/4 of the way down will be lambda over 2. And the path difference between the top ray and a ray coming out 3/4 of the way down will be 3 lambda over 2. Now, what's the path difference between the top ray and a ray 1/4 of the way down? Lambda over 2. What will happen when they combine? Destructive interference. What about this ray and this ray? Again, path difference lambda over 2, destructive. This one and this one, this one and this one, this one and this one. the entire top quarter we can think of as being canceled out by the second quarter. Well, what about this ray and this ray? Between lambda and 3 lambda over 2, that's a difference of, again, lambda over 2, a half lambda. They will cancel out this one and this one, this one and this one, this one and this one, this one and this one. So we can think of basically the top fourth being canceled by the second fourth, the third fourth being canceled by the fourth. The whole thing gets canceled. So when we have this arrangement where the path difference at the bottom is 2 lambda, we again will find a dark fringe. In other words, where w sine theta equals 2 lambda, we get a dark fringe. Are there any others? Well, we'll look at one more. So what if the path difference between the top ray and the bottom ray is 3 lambda? Well, then if we come 1/3 of the way down, the path difference between the top and the bottom will be lambda. And if we come down 2/3 of the way, the path difference between the top and the bottom will be 2 lambda. And then if we come 1/6 of the way down, the path difference is a half lambda. Half of the way down, the path difference is 3 lambda over 2. 5/6 of the way down, the path difference will be 5 lambda over 2. And so again, what do we find? The path difference between the top and 1/6 of the way down is lambda over 2. They all combine destructively. So basically the top sixth cancels. We can think of it as canceling with the second sixth. The third sixth cancels with the fourth sixth. The fifth sixth cancels with the sixth sixth. And again, what do we find? Complete destructive interference, another dark fringe. So when we have this arrangement where this is 3 lambda, we find another dark fringe. So w sine theta equals 3 lambda. Well, I think you see where this is going. Basically, where w sine theta equals lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda, we find a dark fringe at those angles. Now, what about bright fringes? Where do we find constructive interference? Well, as we saw, when we look at the very central point, we have all of the rays traveling at the same distance, so there is no path difference, and we find a bright fringe right at the very center, right on the central axis. So we get a bright fringe there. What about those other bright fringes? Where are those points of constructive interference? Well, the fact of the matter is that while these points we can show as being points where the rays do cancel out and we get dark fringes, the other points we don't have perfect constructive interference. Those are points where we have less destructive interference. So it's not that all of the rays are in phase with each other, it's just that they are not completely out of phase with each other. Which is why those bright fringes to the side weren't as bright as that central bright fringe. They got dimmer and dimmer and dimmer as we moved away because we still have some canceling out, some destructive interference, just not complete destructive interference, nor do we have complete constructive interference. So, for the single slit, we'll only have a single equation describing the location of the dark fringes. We will not have an equation describing the locations of the bright fringes. So, what is our final result here? So, for single slit interference, sometimes referred to as single slit diffraction. Diffraction is the word usually used for the bending of waves around corners, which is kind of what's happening here. We've got this single slit and the waves are bending around the edges of the slit to give us this pattern. What do we have? The location of the dark fringes are given by w sine theta, where remember w is equal to the slit width. Theta is then the angle measured from the central axis. We could say theta is positive if it's above, negative if it's below. That's kind of arbitrary, but that's the way that we've done this. Is equal to m lambda. Lambda is the wavelength of the light source, the wavelength of the laser. M is then, well, what is m? Well, we found that m was 1, 2, 3. Those would be for positive angles. M would be -1, -2, -3 if we wanted to look at negative angles, in other words, for angles below the axis. So we might say, well, m is just an integer, but there's one integer that m is not, and that is 0. For m equals 0, that would correspond to theta equals 0, which would be the point on the central axis, and we know that that is actually the center of the central bright fringe. So we do not have an m equals 0 dark fringe. So we can actually label our dark fringes. The first dark fringe above the central axis, that would be our m equals 1 dark fringe. The next one would be m equals 2, and then m equals 3. And if we wanted to go below the axis, that would be m equals -1, m equals -2, m equals -3, etc., etc. So we have labels for the dark fringes, but not for the bright fringes. And remember, we do not have an m equals 0 dark fringe. Now we might ask ourselves, how wide is this central bright central bright fringe? We noticed that that central bright fringe was larger than the bright fringes on the side. Well, we might ask if we've got an angle theta up to our m equals 1 dark fringe and an angle theta to the below, negative theta, to the first dark fringe below, we can think of the width of the central bright fringe basically as the distance between the centers of the two dark fringes that border it. So we might think of the bright fringe being bordered by those two dark fringes, and then the distance between those two dark fringes would be the width of our central bright fringe. In other words, what would that angle be? Well, it's a theta above, theta below. That would be 2 theta. So how could we find 2 theta? That would give us the width of that central bright fringe. Well, if we could use the small angle approximation, as long as the fringes are basically small compared to the distance from the slits, in other words, compared to L, we can assume that sine theta is very similar to theta. Divide by W, what do we get? We get 2m, we're looking at the distance between the first dark fringes, so that would be m equals 1. So m equals 1, so 2 lambda over W. So that would be the width of the central bright fringe. Now, let's just think about this for a second. Notice we've got something very odd here, something maybe a little bit unexpected. If we remember, W is the width of our slit. If we look at a narrower slit, if we make our little window here smaller, if W gets smaller, what happens to theta? Well, if this gets smaller, theta gets larger. That means that if our window gets smaller, our pattern gets larger. So the smaller our window, the bigger our fringes. The larger the central fringe is in particular. That's a little counterintuitive. We might think that the smaller the window, the smaller our fringes should be, but it's exactly the opposite. The smaller our window, the larger the fringes are. And that's because the smaller the window, the more we're cutting off those side parts of the beam, the more diffraction we get, the more the rays are actually spreading out, which gives us a larger interference pattern. So a little counterintuitive, but very, very interesting. Okay, great. Let's actually take a look at that. Let me show you a couple different slits, and we'll see how the pattern changes. I'll show you a larger slit, then a smaller slit, and we'll see what happens.